Welcome everyone to our First Friday's training webinar series. My name is Steve Temme. I'm the president of Listen, and today I will be talking about advances in impedance measurement of loudspeakers and headphones. Next month on April 4th, Brian Fallon will be giving a webinar on headphones according to the EN 50332 standard, which outlines measuring headphones and portable music players for maximum sound pressure level. Okay, so let's start with theory and motivation. I will talk about the theory behind impedance measurements and why we're having this webinar at all. I'm going to talk about system wiring diagrams and how to set up the analysis step in SoundCheck to make these impedance measurements. I will discuss single versus dual channel measurements, and in particular using post-processing and transfer function algorithms. And I'm going to discuss the significance of the test signals on the final results. And I'll finish with a short presentation of Teal small parameters. Okay, so impedance measurements are very important for R&D and QC. They describe the electrical and low-frequency characteristics of a loudspeaker. Simple and accurate impedance measurements of loudspeakers and headphones should be easy, but very often they are not. Why? Well, for example, repeatability is often a problem, especially from test lab to test lab. It can be due to differences in setups, cables, test levels, and etc. I cannot tell you how many times I've visited customers who are having problems with their impedance measurements, and we'll get into why those problems pop up. The most common and least expensive way to measure impedance is across a current sense resistor in series with the speaker. But this is prone to many errors. We'll get into discussing why some of those errors occur. There is a more expensive and accurate alternative by measuring both across the sense resistor and the speaker terminal simultaneously. Very often we call this a two-channel method, and I'll show you how that can be done. But there are still some caveats that you got to look out for in order to make really good, accurate measurements. And then, is there a less expensive, simpler, and more accurate way to measure impedance, especially on a production line? Well, we have some new products that I want to show you that will make this easier. So let's just review the theory. This is just a simple circuit diagram of a signal generator, V-in to a power amplifier with a feedback loop, and then, of course, the amplifier amplifies the signal to V-out, which gets measured across a loudspeaker and a sense resistor. And if we know the current going through that loop, we can actually measure the impedance. So it's very simple. If we look at this equation over here, it is Vn times the gain of the amplifier divided by the voltage measured across the resistor, the sense resistor, which determines the current. But this assumes a perfect amplifier independent of load and no wiring losses. For example, normally this is done by calibrating the amplifier first without a load, and then assuming that the loudspeaker and sense resistor will have no effect on the output of the amplifier, and that's not always the case. So we have this error in the numerator just due to the fact that the voice coil voltage is actually not just V-out anymore. It depends on the sense resistor, the load on the amplifier, and certainly the size of the sense resistor. We also have errors introduced by the sense resistor. Typically, what happens is this combination of the resistor and the loudspeaker actually lower the damping factor and alters the dynamic behavior of the voltage. And as a result, our sense can also drift due to heating, thermal problems. But it is easy to implement with one single-ended channel. So let's look at that setup. So here is a typical wiring diagram with an amplifier hooked up to a loudspeaker, a load resistor in series with the negative terminal typically of the loudspeaker. You could go across the positive terminal, but you just have to be a little careful in your calculations. And then we have, typically, we recommend a balanced input. And the reason for that is twofold. It will prevent accidental shorting of the amplifier, and it will also prevent potentially blowing up this analog interface or the sound card. So calibration. Calibration is very important, as always. In order to get accurate measurements, you have to calibrate your sound card. You can use the calibration sheet that comes with hardware that Listen sells. And if you don't get the right VP values in there, it could cause errors in your impedance measurements. It's also very important to calibrate your amplifier for frequency response and phase. I will show you later how that automatically gets taken out of the final impedance measurement, so to a certain degree, it shouldn't matter what the frequency response of your amplifier is. And as always, it's very important to use good cables. We want to use low resistance cables and good connections. Otherwise, you end up measuring the loudspeaker and the cables together. And I've seen many cases where people got thin cable running for a very long distance, say into a test chamber, and then the test equipment's on the outside, and it can be even a couple of ohms with the cable, and you end up measuring a 4-ohm loudspeaker. It looks like 6 ohms because of the cable in front of it, the speaker cable. And after you've done a calibration, the best thing in the world is to just measure a known resistor. Go find a decent wire-wound resistor, for example, 4 ohms, hook it up across the output of your loudspeaker, and measure the impedance, say 20 to 20 kilohertz. You should get a perfectly flat line at 4 ohms. If you're not, something's obviously wrong, and most likely it's the calibration. And as I like to say, it really is that simple as long as you follow those step-by-step procedures. So Listen makes an impedance box in order to simplify the setup. It comes with a standard 0.25 ohm wire-wound resistor, low inductance, high power. Now, whenever we're measuring impedance on a loudspeaker, and we're using Ohm's law to measure the voltage drop across a resistor, we want to make sure that the difference in voltage across the speaker and the voltage across the sense resistor isn't dramatically different. Otherwise, we will get a lot of noise. So as a general rule of thumb, I suggest the reference resistor should be 10 to 100 times less than the loudspeaker. It could be 10 to 100 times more, but then that's going to affect the voltage across the loudspeaker. So keep that in mind, especially when you see noisy impedance measurements. It also comes with a balanced TRS connector across the reference resistor, as I mentioned earlier, that will help prevent ground loops and shorts. And it uses low resistance wires and connections. So it's simple and expensive, but it's not foolproof. So in the analysis settings for SoundCheck in the step editor, obviously we're going to have a stimulus step with some sort of sine sweep. We're going to have an acquisition step where we measure the signal across that sense resistor. So that's going to be the response or the recorded time waveform you can see from the impedance box. And the stimulus is just going to be the stimulus that is actually coming out of the sound card. So again, it's just a one-channel measurement. We're just measuring across the sense resistor, and we've already calibrated so we know what voltage is coming out of the amplifier for a given stimulus. So there's some assumptions there. On the electrical tab, we want to choose impedance. And if we choose impedance box, it will default to a 0.25 ohm resistor. You can use a custom resistor if you want. And as you can see, the wiring diagram kind of indicates the physical connections. So pretty straightforward. Now, one other thing I want to point out is, again, that assumption I made up here. If we look at the apply correction out, so that's assuming that we calibrated the amplifier. And what that does is it takes into account both magnitude and phase response of the amplifier and divides it out of the measurement, so that when we measure the impedance, we're actually truly just measuring the loudspeaker's impedance and not including the amplifier's response. So if you check that, it will correct for it. If you don't, if your amplifier is not perfectly flat, you might see some slight differences. So an alternative is to actually measure the terminal voltage across the loudspeaker at the same time as measuring the voltage across the sense resistor. This has a couple of huge benefits. So basically, our impedance calculation now is just going to be V out minus V sense, which is the voltage across the loudspeaker. And again, it's divided by the current V sense over R sense. So pretty straightforward. So this eliminates errors in the numerator. So the voice coil voltage is actually V out minus V sense. As I mentioned, we're measuring at the speaker terminals. Closer to the speaker terminals, the better. That will eliminate or compensate for wiring losses. It still won't compensate for bad connections, so you still need to take care in how you connect your clip leads or whatever you're using to the wires. And most importantly, it will compensate for non-ideal amplifier behavior, because as that amplifier's performance changes over frequency due to the potentially the load of the loudspeaker, we're measuring essentially the response of the amplifier and subtracting it out. But we still have errors due to the R sense, or the sense resistor, such as the thermal heating and the loading of the amplifier. The combination of the loudspeaker and the resistor is not entirely known, so that does cause some potential errors. And of course, we're giving up an extra input channel in order to measure simultaneously across the sense resistor and the loudspeaker. So this is probably more ideal for a research and development lab, and not as ideal for a production line, where they typically will use one channel for measuring the acoustic response with a microphone and the other channel to measure the impedance. So the wiring diagram is very similar. The only difference now is the second input is measuring across the loudspeaker. So because it is a two-channel measurement, we're going to actually be measuring either the transfer function, where we're going to be measuring one input versus the other input. In the case of the loudspeaker terminal voltage versus the resistor voltage across the resistor. And if we use post-processing, we can just do that as an extra step. That's pretty simple. It doesn't work so well under certain circumstances, depending on the type of signal you're using. The transfer function, it works extremely well if you're trying to use things like noise or MLS signals or even multi-tone. In fact, you could even use speech or music if you wanted. That would be very difficult to do with post-processing, but it is possible. The other advantage of the transfer function is there's a coherence indicator, which will tell you essentially about the signal-to-noise of the measurement. We, in a newsletter, posted some example sequences using these two methods, as well as a write-up covering a lot of what I'll be talking about in the seminar. So you can get that on our website, and I suggest you go grab those if you haven't tried them. So the analysis settings for the transfer function is a little different. The main difference now is the stimulus is actually the waveform going into the loudspeaker. So that's going to be typically input 1. And the sense resistor is the same. We're just going to measure the voltage across the sense resistor and divide the two in a transfer function. Over on the electrical tab, it's a slightly different setup. We're going to be selecting Amp Connect or SCAMP. I'll show you that a little bit more later. It's a slightly different wiring configuration, so the calculation's a little different. Both Amp Connect and SCAMP have, by default, either a 0.1 ohm resistor. I'll show you in a second, as part of the feedback loop. And Amp Connect also has the option for Z-High, which is 1 ohm by default, or you can even put in a custom resistor. So now I want to show you a technique where we can essentially eliminate some of the variabilities of the sense resistor. And what we do is, instead of having the sense resistor in series with the loudspeaker, we actually put it inside the feedback loop of the amplifier. So you can see it here now. This totally isolates it from the loudspeaker outside. And it has several benefits. So we still get a voltage. In fact, we get a voltage, a particular sensitivity to the current due to the sense resistor. So we get, just like we did before, we get the voltage out is actually the signal going into the amplifier times the gain. But the current is all calculated inside the feedback loop of the amplifier. And this has several benefits. So because of the negative feedback, we've isolated the voice coil from the sense resistor. We've applied for a patent on this. And it's, as I mentioned, it's used both in SoundCheck Amp, SCAMP, as well as Amp Connect. It eliminates the some errors due to high damping factor, because now the output impedance of the amplifier can still appear like 0, where if we got a loudspeaker and a resistor hanging on it, it can be adversely affected. And we preserve the dynamic behavior and the V-sense accuracy, as well as we can minimize any resistance drift due to temperature, because we now have kind of a very controlled environment. However, we're still using one channel, and we're still not taking into account wiring losses or the cables to the loudspeaker. So it's not perfect, but there is a way to minimize that, and that, again, is just to use 2 channels, one to measure across the loudspeaker at the same time. And again, preferably you want to measure right at the terminals. We now have 2 simultaneous measurements, the sense, V-sense, as well as the voltage across the loudspeaker. And channels can be single-ended since the speaker is grounded. So I'd like to show you some results that we've measured using different types of methods. And the particular loudspeaker we used for this demonstration was an 8 ohm bookshelf loudspeaker. We are applying 1 volt RMS. We swept from 20 hertz to 20 kilohertz. And for now, I'm just going to show you the magnitude of the impedance, although SoundCheck almost always is measuring the phase as well, the complex phase. And I'll show you both the simple single channel, simple dual channel, and then what I'm calling the improved single channel, which is using SCAMP. So if you look at the measurements, you can see, first of all, that the simple single channel is a little bit higher than the dual channel. And that's even though we've calibrated out the reference resistor. As I mentioned, you know, the loudspeaker can load the amplifier slightly differently. So we get pretty close results, you know, well within, probably within an ohm. but we can do better. And if we look at the simple dual channel versus the improved single channel, we actually see we're starting to get very similar results, even though we're just using one channel. So as I mentioned, we get very good correlation between the dual channel simple and the single channel improved method. Now I'm going to zoom in on the resonant peak. This speaker had very high Q, which makes it a good test subject because it's going to be more reactive. You'll notice that the Z max for the simple method single channel was 42.8. We use the dual channel, the reality is 41.9. And then, curious enough, when we look at the improved single channel, we get 40.5. And what's going on here is that both simple methods are overestimating the impedance, the Z max. And this is probably due to the lower damping factor as a result of the back EMF from both the speaker and the load. So the back EMF is proportional to BL and voice coil voltage, and is also going to be affected then by the complexity of the load. So even though we're measuring a speaker, we have to remember that we're actually measuring a speaker with a resistor in series using the simple method, and it's not going to be the same thing as measuring the speaker by itself. Okay. So basically, this reduces the current, which is part of the reason that the Z max is lower. So we get an overestimated impedance. So the other important thing to take into account when you're making impedance measurements is what stimulus are you using? And not only what type of stimulus, but more importantly, what level, test level. So when we go to measure the impedance, we're actually going to be affecting the dynamic performance of the loudspeaker depending on how much voltage we put into it, how much energy. And what happens is you'll see that as we put more energy into the loudspeaker, typically the resonant frequency will decrease as the stimulus level increases. The Q will go down, the Z max will go down. So it's quite obvious. I'm going to show you a bunch of measurements in a second. But I just want to point this out because a lot of times I see people comparing impedance measurements at different levels. And Dick Small, who was one of the inventors of the Thiel-Small parameters, always joked that small didn't stand for his name, it stood for small signal. Because basically, Thiel-Small parameters are a linear model and assume linear behavior in the loudspeaker. And that only happens, and it doesn't really happen unless you have a very low level signal going into the loudspeaker. The other thing you'll see is if you try to compare, for example, different type of test signals like MLS versus sine sweeps, you also will get completely different results, and that has to do with the energy and how it's applied. A sine sweep has a very concentrated energy at one frequency at a time, where a noise signal like MLS is spread out over the entire bandwidth. So you have different energy spectral densities, and for the same reasons, nonlinear behavior, you'll get different results. So keep that in mind, especially when so many people historically had used MLS to make these measurements, and nowadays a lot more people are using continuous sine sweeps. So here's an example that a customer sent me of 4 different types of loudspeakers of varying performance. And you can see, if we just take the first one here, at 10 millivolts, excuse me, we're getting roughly a resonant frequency around 280 hertz. And the Z max is roughly around 30 ohms. And as the level increased by 6 dB, a factor of 10, look at the dramatic shift here. All of a sudden, the resonant frequency has dropped, and the Q has gone down, and the Zmax has gone down. You go up to 1 volt, and the thing is like a completely different beast. It's got a resonant frequency of 200 ohms. So clearly, that's going to affect your Teal small calculations, and also what you end up with as a box design based on Teal small parameters. Some speakers are better than others. If you look at this one down here, it seems a little more stable, but it then does reach a point above 1 volt where it starts to shift. And basically, these are all just nonlinearities. Some have smoother thresholds, some have more step functions. So, speaking of Teal small parameters. So Teal small parameters are a set of electromechanical parameters that define the specified low-frequency performance of a loudspeaker driver. Using these parameters, a loudspeaker designer may simulate the low-frequency acoustic response of a given loudspeaker driver in a given enclosure. So basically, we can measure the impedance of a loudspeaker in a couple of different ways, and from that, we can actually model the low-frequency performance. Keep in mind, though, it's really only useful for around resonance and below. It's going to do nothing for you above resonance, typically. So to find these parameters, the impedance of the driver, for example, resonant frequency Fs, max impedance, Zmax, and the quality factor Q, must be measured and calculated, typically with 2 measurements, such as added mass or a known volume. So if it's a big speaker, like a home speaker, you can probably get away with added mass. If it's a micro speaker, good luck. First of all, the mass of the diaphragm is probably so small that you're going to have a hard time putting a mass that you can weigh on it. You might not even be able to get into the volume to even put it there. So typically for micro speakers, people use known volume. In some cases, people will measure it directly with a known driver mass. They know what the cone weighs, and they're measuring the same type of speaker over and over again, or they measure it directly with a laser. But those tend to be a lot more expensive approaches as the laser. But you can use a laser with SoundCheck and calibrate it and do it that way if you wish. So part of calculating the resonant frequency, the Zmax, and the Q requires us doing a curve fit. In SoundCheck, we use the post-processing editor scalar type, and we choose what's called operation estimated resonance. So what this algorithm does is it applies a simple curve fit. It's a least squared algorithm, least squared fit, and to the impedance curve to derive F0, Zmax, and Q. In order to do this, it needs to know a search range. In other words, if we have a impedance measurement with multiple resonances, we need to tell it which resonance to look at. Typically, it's the lowest, but it can be, depending on the venting of the loudspeaker versus sealed, we may want to put a search range very carefully around where we expect the resonance to be. Then what happens, a lot of people get confused by this parameters, this -3 dB. Neville Teal, when he did all his papers on calculating these parameters, he used a very simple approach, which was the half power point, which is -3 dB down, and he made sure, or he hoped he had enough frequency resolution that he actually found the -3 dB point. Well, with a curve fit, you don't need fantastic resolution. It can do extremely well even with 6-octave resolution typically, which is ideal for a production line, because then you don't spend a lot of time measuring low frequencies that really are pretty well behaved. So the -3 dB in this case is actually the width control. So once it finds the peak, it's going to look minus 3 dB down below and above the resonant frequency. And then it's going to use that region to curve fit. Now, there's a problem if you have a low Q driver, such as a tweeter. There very well may not be a minus 3 dB down point because the Q is so low and the curve will just flatten out. In those cases, you want to use something like minus 2 dB or minus 1 dB. And in general, you always want to curve fit or have the start and the stop of the curve fit be on the point of the curve that's steepest. In other words, you don't want to curve fit when the curve's flattening out because you'll actually have more noise in that portion of the curve. Where if it's steep, the difference between two frequency points will have less effective noise. So keep that in mind when you're using this algorithm. Sometimes you'll see NAN, it can't calculate it, and typically that's because it couldn't find the minus 3 dB down points, and you need to change it to something like minus 2 or minus 1. Okay, let's do a demo. I'll just take 1 second for me to share my SoundCheck 12. It should flash up on your screen in a moment. All right, well, hopefully all of you are seeing my SoundCheck 12 screen now. So, and SoundCheck 13 is coming out soon, but I didn't want to show it to you because it hasn't officially been released. If you go to the loudspeaker sequence folder up here, you'll notice that you have a choice of teal small parameters. You have a basic impedance measurement, it's a single channel. As I mentioned, you can download the one for transfer function and post-processing, 2-channel measurements. I recommend you do that if you want to get really good accuracy. And you can choose, for example, added mass, known driver mass, or known volume. So I'm going to use added mass. That's pretty popular. And I just hit start. Now it's going to walk me through and ask me some questions. Do I want to recall stored impedance curves, because maybe I'll go off and measure them, and then I'll play around with my teal small calculations in my desk. I'm going to recall some impedance curves since I'm not going to bore you with doing the measurements here. And it's going to ask me the driver diameter in centimeters. It actually uses that to calculate the radiation efficiency. Maybe not the most useful calculation in the world. And now it's going to ask me for the DC resistance. And that's important when you do these calculations. I won't get into a long explanation about that, but it is fairly significant. The minimum impedance will very often be very close to the DC resistance. I suppose there are some exceptions, not that I'm such aware of, but granted, it will not be quite as accurate as the DC resistance. It might be slightly higher. Let's just use it for this one. You could use a voltmeter to measure the DC resistance, or you could use a audio interface that actually is DC coupled, like an iCard. Then it needs to know the weight of the mass of the weight in grams, and then it chugs through and it calculates all the teal small parameters. And you can see the two impedance curves here. So there's one, the blue curve is without the added mass, so that would typically be the first measurement. You can see the estimated resonance after doing the curve fit is 79 hertz. And the Zmax is 6.93 ohms. Actually, I'm looking at the wrong thing. And the QES and some of the typical parameters that make up the teal small parameters. The second, the green curve, is actually where we've done the added mass. And okay, I see what I did wrong. Yeah, the 6.93 ohms is actually the minimum impedance. The green curve is now with the added mass. You notice that you got to be a little careful. The added mass can do some funky things to the impedance curve. In fact, it's introduced this little resonance up here, so I want to make sure I do my search range and don't include that. It could slightly throw off the curve fit algorithm. And as typical, the resonant frequency should drop, and the Zmax should shift down or go lower as well. So let me just show you the sequence real briefly and how this is done. So you can see there's quite a few steps involved, post-processing especially, and also the estimated resonance, as I mentioned earlier. There's also the actual equation editor for calculating the teal small parameters. Now, you could do this in probably 100 or so post-processing steps, or you can do it with one step using the equation editor. It's kind of like MATLAB. You could even, if you prefer, just dump the data directly into a program like MATLAB or one of the teal small parameter programs that are out there for doing post-processing. Anyhow, it's very convenient to do it here. It's also extremely fast if you need to do it, for example, on the production line. So you have a bunch of variables, and you write your equations. This is a very simple teal small formula. You could make it more complex if you wanted, to take in things like added capacitance models, inductive models. But this should do the job for most people. And if I hit apply, it then goes and it calculates based on different inputs. For example, the mass I was entered by hand, where the resonance is it measured, and then it performs the calculations of things like the equivalent volume, the moving mass, compliance, so on and so forth, BL, QTS. Now, one thing that's kind of nice, most test systems kind of bury this under the hood. They don't actually show you the equation. They don't let you play with it. We can actually go in here and modify this on the fly if we wanted to. We could even say what-if scenarios, like what if the DC resistance wasn't 6.48 ohms, but it was, I don't know, 7. So I just go here and say user-defined constant, and I'm going to enter 7 instead of 6.8. And then if I hit apply again, it will update all the outputs. So we'll get slightly different results. So that could be handy. In any case, as I said, it's a very convenient way to do it. Okay. So let's just go back to the PowerPoint for conclusions. So, as I always like to remind people, calibration matters. It's a necessary evil. If you don't calibrate, you're not going to get absolute measurements, and you might not even know what you're getting. Use a reference resistor. Make sure it makes sense. Good cables and connections matter, and again, all the more reason to use a reference resistor. If for some reason you have good cables and good connections and you measure a 4-ohm resistor that's not for ohms, then you have to ask yourself, is it my calibration or is it my cables or both? Test signals and test levels matter. As you saw, it can have a dramatic effect on the resonant frequency, the Zmax and the Q, and adversely affect the teal small parameters. And the improved method, where we actually have the sense resistor in the feedback loop of the amplifier, really does improve things dramatically, both in terms of accuracy and reliability and simplicity. It now means that on a production line, you probably can get away with one channel as long as you have decent wiring and not worry about things such as, is my sense resistor heating up or what's going on. So as I said earlier, the accuracy at the first resonance is more pronounced since the damping factor is not compromised. It is accurate in frees up an acquisition channel, so you could do acoustic measurement on one channel, electrical on the other. And if you would like more details, as I mentioned earlier, you can go on our website and download a tech note on impedance measurements, as well as an AES paper that we presented in New York last year at the 135th convention. I believe we can now put that up on our website now that it's been 6 months, almost 6 months after the convention. So we're happy to supply that to you guys as well. Okay, I guess I'll just finish with a quick little sales pitch for SCAMP. So both SCAMP and AMP Connect have this zero output impedance, or virtual zero output impedance with the sensor resistor inside. You notice on SCAMP we have the sense output here balanced out, so that would just go into your other input. It also has a couple of neat features, such as it can do a DC bias, and if you wanted to look at nonlinear behavior or voice call centering of your loudspeaker, you can actually apply a DC offset on top of your AC signal. It's also extremely compact, and it's CE approved. Okay, well, I want to thank everyone for coming, and if there are any questions at this time, I will take a look at them and see if they've all been answered. I just want to thank everyone for coming, wish you a wonderful weekend, and if you would like to see this webinar again, it will be uploaded to our website probably beginning next week. You'll be able to watch the video. Thanks for attending, and I hope you can make it to our next one, April 4th, on headphone maximum output sound pressure level.